our next category of materials out in the solar system will be the comets. And they're the number one way to identify these comets is their gorgeous tails trailing behind them. So a comet is going to be icy planetesimals. They're not going to be so much of rocks and metals. They're going to be types of ices. And they generally fall into two types. The types that orbit from around the Kuiper belt, and those that come from the Oort cloud surrounding the solar system. So as a reminder, the Kuiper belt generally falls in a range of about 40 astronomical units, 30 to 50. So we'll split the difference and call it 50. And so there are comets that fall from the Kuiper belt, or others that fall from the Oort cloud, which I'm just going to pick a value and say it's about 1,000 astronomical units to the limits of the Oort cloud out there. The comets from the Kuiper belt, they're going to fall into this category of short periods. And this will be periods of less than a few centuries, decades to 200, 300-ish years. What this means is that these things tend to be close to the ecliptic plane. Right? If this white line here represent the ecliptic plane, they're going to have orbits that swing around like this, coming through. Halley being a bit more the extreme one out there. So the short period comets are, compared to the other type of comets, are constantly whipping around the sun. And so one thing we'll start to talk about is how their nuclei are worn out compared to the other types, the long period comets. So what makes it a long period comet? They'll have periods of thousands to millions of years. For a long period comet, when they swing by, you get to see their beautiful tails flowing from the sun, and they go away. You won't see that for thousands of years. So these long period comets, they tend to come far out from the Oort cloud, and they'll have extreme tilts. Let's go back a bit. Focus on Halley. Here's Halley comet coming in through our ecliptic plane. Now, here it is again. Right? So these long period comets will basically dive bomb down through the solar system and whip out away. They're not around the sun for most of their lives. They'll be cruising along just fine for literally thousands of years, and they'll pass by hours, matter of hours, and then they'll just be gone. And they'll fly off out towards the Oort cloud again until gravity brings them back down. So we'll discuss is that these long period comets have nucleuses that have not been worn out. And what we'll establish in a bit is that what's producing the tails around the comets is the sunlight literally melting them. So when you're not around the sun very often, you just don't get melted. You don't get worn out very often. So here's a picture of a comet when it's far from the sun, not close to it. And I would say that it's this mixture of ice and rock, or as I like to call them, dirty snowballs. Just a lot of material there, just kind of the rock glued together by the water. Well, I guess ices. So the nuclei of these comets will range from a few dozen meters to maybe hundreds of kilometers. Remember, these come from potentially planetesimals. This image here is of Comet 67P of the Philae lander as it was approaching, and then here once the lander was on the comet. And so it's this very jagged, red, crazy shape. Now let's zoom out and let's bring that comet close to the sun. When it's near the sun, we call it an active comet. And one thing we'll notice here is that there are in fact two tails for the comet. There is a ion tail and a dust tail. We normally only think of things like the dust tail, but they're both there. They're both stacked on top of, well, not on top of each other. It depends on the orbit. But there are, in fact, two tails associated with an active comet. What's happening is that as the comet is approaching the sun, which for this diagram, the sun would be down here, as they're approaching, it's getting heated up, warming, melting a little bit. Some of the layers are going to start sublimating, going from a iceous state to immediately a gaseous state. And so that sublimation will form the coma and the tails. So let's go through this. The nucleus. That's what we saw literally on the previous slide, that rocky terrain with the ice gluing it together. As it starts to approach the sun, turn into an active comet, you'll have this coma around it, producing the ion tail and the dust tail behind it. Breaking down the two tails in a bit more detail. As the comet is approaching, going around the sun, yes, we have the ion and dust tail. For a quick reference, the ion tail by some resources gets also called the gas tail. But regardless, the ion tail is produced by the solar wind acting on the ions of the nucleus, basically any of the charged matter. So the ion tail itself is always going to point radially away from the sun. Anywhere the comet is when it's active and near the sun, the ion tail is pointing at the sun. The ion tail will point towards where the sun is relative to the comet. Whereas the dust tail is the material that got liberated, pushed, freed from the comet's nucleus. And so the dust tail will be a trail that's following the motion. If this comet is going this way, this tail will be the remainder flying around. At this point, here, let's go ahead and draw this. At this point, the comet is going that direction, and here's its corresponding dust tail. Comet's whipping around that way. Some material's going off that direction. So the dust tail is bending around, trying to follow the path of the comet as it orbits around the sun. And just for reference, because we always have excuses for pretty pictures. Here's Comet McKnight, right, one of the brightest comets that we've seen in many years, as it flew through the night sky. Finally, like all things in the universe, how do we study them? We hit them. This is great pictures of an object, a spacecraft that we sent to hit Comet Tempel 1. And so we picked out this impact site and had taken images. This is far away, before our craft had smashed into it. And here it is during the impact, obliterating, liberating a lot of material flying off of this comet. Things we want to observe is what's contained in the comet. What's its chemical composition? Think about what the comets are. They're remnants of material, say, from the Oort cloud or from the Kuiper belt, the far-off stuff. This stuff is not very active. Same thing goes for the asteroids. So when we study things like comets, like asteroids, we get an inkling, a sense of what the material was like at the beginning of the solar system, back when it's still a nebulous, slowly forming into planetesimals, planets, and the sun at the center. So by hitting these comets, by learning about the percentages, the ratios of material in them, we get to learn about the ratio of materials just in the total solar system.